So if you didn't notice, you can see your score on Canvas now. The scores are up. So your raw score out of 150 points, which is adjusted to 1%, and then your adjusted score as a percent. Okay, so you can see exactly what you got. All right, so let's look at this function. So here's a complex function here. It's a polynomial multiplied by an exponential function. And I want to build a accumulation of arc length. And so what will that be? So for any x from 0, the function will tell me how much arc length, how long the arc length is to that value of x. Right? So if x was 1, what would it tell me? It would tell me the length of this curve, this like steep hill, right? So if x was 1, it would tell me how far you would walk up and down the hill, back to 1. Okay? If x is 5 in the function, it's going to give me the length of this whole red curvy arc to 5. So can you write that function? What should I write in GC to create that function that's going to tell me how much arc length along the red graph for any value of x? So this is kind of a test from last time. Can you do it? So we call that little s. We're going to call that little s of x. So if I want to write the arc length function, what do I need to write the arc length accumulation function? Mark?
The integral from 0 to x.
Okay, so before we actually do it, so what's the one thing that I need to do it? You should be thinking the rate of change. It's the same thing over and over and over again. Every quantity we've talked about, unsigned or signed area, volumes of revolution, now arc length, and then today we're going to start surface area. All these things, these quantities that we're going to accumulate. To write the accumulation function, we start with, or need, rate of change function. The rate of change function. So, Mark, go for it.
Okay, so square root of, the integral from 0 to x.
Uh-huh.
And then the square root of 1 plus t to the 5th. The derivative of.
Yeah, so this is this product rule, really ugly product rule. So this is the beauty of GC. What can I do?
ddx.
Right, so I can just use total derivative. Have it do it for me. Of?
T to the 5th, parentheses, t to the 5th, minus.
Yeah, so then here's the beauty of function notation. No, I'm so glad you started saying that, because we could write that formula out, right? dx of that thing. But what's much better?
F of x.
Yeah, right? And we want to use t's, right?
Square that.
That's right. And dt. And what's that whole thing in that whole square root? What is that thing? The whole square root. The rate of change of arc length, which we derived last time in class, right? It's just a rate of change of arc length. Rate of change of arc length. Same pattern. Okay, so now what did I say? I wanted to find, if I want to know the height up and down the hill to x equals 1, how can I find that value? S of 1, that's it. Do I have to write S of 1 equals integral from 0 to 1, blah, 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 blah? No. But lots of you guys did that on the test when I tried to emphasize. Make it as concise and short as possible, right? All you need is S of 1. That's it. And then GC tells you what the answer is. S of 1 is the beauty of it is it represents what? The arc length when x equals 1. You don't have to rewrite the integral. Yes, sir?
Sorry, did you say total derivative earlier?
Yeah. Well, it's as opposed to a partial derivative, which you learn in Calc 3. So just don't worry about. So total derivative is just derivative as you know it. Yeah, partial derivatives is what we learn later. So just ignore partial derivative. Total derivative just means derivative. Yeah. So if you look. Yeah, just don't do that because that's for Calc 3. Okay. Okay. So what does that mean? What does the 6.85 mean? length of the curve when you get to x equals 1, starting from 0. Okay? And then suppose I want... So that's the length of the curve, starting from 0 all the way to 5. All right, so how far is it from, say, 2 to 4? So say I want to start from here. I want to hike up the hill, back down to sea level, and then down to the valley. So from 2 to 4.
Just do S of 4 minus S of 2.
Oh, you're so smart. S of 4 minus S of 2. Okay, so 2.196, if these are miles on the x-axis, that'd be 2.196 miles up and down that hill to the bottom of the valley at 4. Okay, starting from x equals 2. All right, so what would be another way to get this value? What would be another way to get this value? Yeah? What's that? Yeah, so what if I changed my function to start at 2 instead? If I had this function starting at 2 instead, then what would that value that we just calculated be, S4 minus S2? How would I represent that? If there were a 2 here instead of a 0, then I would just write just S of 4, because then now my accumulation for S is starting at 2. So if I just wrote S of 4 with a 2 where the 0 is, then I'd get the exact same value here, 2.19647, okay? So what we want to do is introduce a new way to make this a little more generalized. Instead of having one argument here in the parentheses, we're going to have 2, and we're going to have the starting value and the independent variable x. Okay, so we have the starting value and the independent variable x. Now, how do I have to change my function to match that? Yeah, so now I'm going to do this with a. And so now I've just made my... instead of having to change the function every time I want to change the a value, I can do that within the function notation now. See that? Yeah.
When you type that comma, did you have to do any other buttons? Because mine was not letting me do that.
It should. So you sure you had Control 9 for your parentheses?
Yeah.
Maybe
it wasn't.
Yeah. So
Okay.
make sure you have the Control 9 for the parentheses, but you should just a comma x comma as many commas and variables as you want. Okay, so now that I've defined it this way, notice that none of these values are showing up. So originally we had S of 1. What does this have to be now to get that value? 0, 1, right? That was 0, 1. And then this one? 0, 5. And these are the values we got before. And then 0, 4. And 0, 2. It's not going to like it. But now if I ask, so that's what we did before according to the new function. But now if I asked you, what's the distance along the curve from x equals 2 to 4? You wouldn't write that. What would you write? S of 2, 4. See, so it's a lot more convenient to have the 2 argument function notation. So I can just change that starting value right on the fly and don't have to change the whole function. And it's the same answer, right? It's the same thing. Okay, now what if I did this? What if I wanted to start at 1? If I was thinking about starting at 1 and I wanted to get the difference between, let's see here, let's mess this up. When I fix the function, is that going to give me the same value or a different value? So now what is this saying? This is saying start accumulating from 1 out to 4 minus start accumulating from 1 out to 2. Will that give me the accumulation from 2 to 4? Yes or no? Some people are nodding. Do you believe it? So if you think about all the accumulation out to 4 from 1, all the accumulation out to, and subtract away all the accumulation from 1 out to 2, what's going to be left? From 2 to 4. So that also should give me. So it doesn't matter what the starting point is. If you're doing a change in a quantity, you can start anywhere you want, and that first amount will get subtracted off regardless of where you start. So now if I fix this function, there it is. It doesn't have to start from 0. You can start from any value using the difference, right? Using the difference approach. Okay? You can start from any value as long as you start from the same value, you'll get the same arc length. But then that's, of course, that's the easiest, right? The easiest is to just start at 2 and accumulate to 4. Okay, the arc length function. What would it look like? What would you think this, if I were to graph the arc length function for this red function f, what would that look like? Straight line? So as x changes, would the arc length increase at a constant rate?
No.
So it's going to increase, like right at the beginning, that arc length is going to increase a lot faster per x than, say, around 4. Do you see that?
Yeah.
So it's not going to be a straight line, but what will definitely be true about it? Will it ever decrease? No, so it'll always increase, right? But it'll increase at different rates. So let's do that just real fast. So how do I graph the arc length function then? Y equals S of?
0, x.
I need 2 arguments, right? So 0, I want to graph it starting from 0. And now I have to, in order to see this, so what is that showing? Y values on that graph correspond to, so like if I come here, I click on this, so I got a Y value of 11.26384 for this X value. What does it mean?
4.8 from 0
At 4.7348. The Y value of this graph, this Y value right here, is the arc length to that X value on the red graph, right? This is the arc length function for the red function named f. So the Y values on this graph are telling you how far you would travel, or the arc length on the original graph. That's you keep going up and up and up. Because so then it becomes kind of constant Y, because we don't have these swings, right? So it's going to be mostly constant as this thing flattens out. Okay, that's true. You don't have to pay me for that. Okay. All right, so let's talk about surface area. So we're going to generate surface areas the same way we generated volumes by revolution. Okay, so I got this function here, this red function. Can you imagine if you rotated that around the x-axis, you'd get something like this. So like a bumpy bugle or something, a bumpy megaphone. Okay. So what we want is a function that, for any value of x, gives the accumulated surface area. So we're not filling the shell anymore, right? With volume, we filled the shell with cylinders, and we tracked the accumulated volume of the cylinders inside. But now we're going to track how much surface there is on the shell itself, right? We're just going to stop at the shell, and we're going to accumulate how much area along the shell, as in this case, as x increases. Okay, so we're going to ask the same question again. If S is the surface area, so this would mean, what would this mean? Capital S is for, little s is for arc length, capital S is for surface area. What would capital S of AX mean? And then can you write a general rule for what that will be? Everyone do it. Take a minute. Here we go. Let's regroup. What does S of AX mean? What does it mean? Yes, sir, Nick.
S of A to X means the surface area from where we start point A to any general point X.
Good. Right. So it's the amount of surface area starting from our fixed starting point A to any value x, right? It's a function, right? So as x changes, we get more and more surface area. This will also be also always increasing function, right? It's always going to increase. There's no signed surface area. There's no negative, right? Always positive, always increasing. Okay? And then how can we write Not doing any math. Forget about what the fact that this is surface area. Just what can we write down that's going to be equal to the surface area function? What will it be? I want to write down what the structure of that function is going to be. What is that? What's that function going to be? Without doing any math about surface area or trying to figure out. Is that what it's going to be?
So don't worry about any math on surface area.
But it's a surface area accumulation function. Therefore,
We need a rate of surface area.
it's equal to the rate of change.
Equal to the summation of
Summation of the rate of change, kind of. Integral, right? Integral, right? Integral.
Yeah.
From a to x of the rate of change of surface area dt. So one of these times we're going to get it, right? That accumulation function, integral from a to x, rate of change, dx, and then we use t's. Okay, so then this is, of course, again, our goal is figure out the rate of change. Here we go. What's the rate of change of surface area? Once we've got that, then we can just write these functions down and let GC do all the work for us. So let's go back to our football example. Remember that this is the function sine x from 0 to pi. We're going to rotate that around the x-axis and get our football. Okay, and then you can imagine x increasing, and then we're going to accumulate surface area along the football as x increases. That's what we want. So what do we say about these geometric examples? So like when we looked at accumulation, we said the rate of change, in this case, what was increasing? And this for the volume, right? For volume, what was increasing? Height, right? The height of each cylinder was increasing. And then what was the rate of change? And what did it end up being? If the height was increasing.
Pi times the radius out.
No, more generally, area of the base, area of the base. When the height increases, it's the area of the base. And where is this volume increasing? Where is the accumulation happening? The leading face is the area of the base, right? So it's that base is where that base shape is where the accumulation is happening. And we said the rate of change was like the size of that. If x grows a little bit, how much more volume are you going to get? You're going to get that much more, right? So it's the leading face, the leading edge is the rate of change. So when we're talking about surface area, it's not going to be that area anymore. What is the leading edge or the leading face? So what's leading that's sweeping out surface area? Which arc length? Right, which arc length? So f of x. So what is like, how is the arc surface area being formed? Where is the surface area being formed here? What's that? What's that? He said the outer edge of the circle. Do you see that? That's where the surface area is growing or sweeping out. And what did we say? We said the rate of change is the size of that, right? So what is the size of that? 2 pi r, right? 2 pi r. So could the rate of change be of surface area be 2 pi r? That would go along with what we've been saying. That the magnitude of the thing that's like sweeping out what's accumulating, in this case surface area, the magnitude of that is the rate of change. So if that's the case, then what is r? We need to know what r is. What's r here? In terms of x, y coordinate. Which is sine x, right? So could it be that our surface area rate of change is 2 pi sine x? All right, so how can we check it? So we can check it with, instead of doing this football based on a sine shape, let's do it on something we know. So we're going to form the surface area of a sphere, and that we can check because we have just a formula for that. So we'll hold on to this. So we think, our conjecture is that the rate of change is 2 pi sine x, and that could form our surface area function. But we want to check that out. So let's look at this instead. So this is too big. What it is? Yeah. So this is the circle function, a 9 minus square root of x, or x squared, which is a circle of radius. What is that? Radius 3, right? This is the top half of the circle of radius 3. So if I were to accumulate surface area from 0 to 3, what would that be in terms of the radius or the surface area of a sphere? Would it be the surface area of a whole sphere? If I went from 0 to 3? Would you say those should be half? All right, so let's start with that. We'll start with half, and we know what that is. Anybody remember the formula? 4/3 pi r cubed is volume, and then surface area was 4 pi r squared. So our radius is 3. We want the whole sphere? Yeah, take the whole thing over 2. Okay, so we're going to set up the surface area accumulation according to what we thought that so what do we do first? I'm going to set up a surface area accumulation function. First I need the function, right? Which is, it's a circle function. 9 minus x squared. Okay, what am I going to need next? So I'm trying to develop the surface area accumulation function. The rate function, right? So I'll call that R sub capital S. And what did we think it was? So we think it's the perimeter or the circumference of each of these disks, right? That's what's growing and sweeping out area, right? So 2 pi, what can I write here? 2 pi f of x, right? That's the radius, f of x, y coordinate. And then I'm ready to write my surface area function, capital S of a comma x, integral from a to x, that's right, R sub capital S of t dt, right? Moment of truth, what I'm going to enter in here to check to see if our rate of change function was right. We thought it was 2 pi r, the circumference of the circle, sweeping out area. What do I write to check that out? I'm going to start at 0 and go to 3, and that we're hoping that that's, what, half a sphere. It's not close, actually. We're off by 12. Close would be 56.3 or something. What's that? Mm-hmm. No, because we're doing the circumference of the circle, 2 pi r, right? 2 pi r squared is the area, but we want the circumference 2 pi. So there's nothing wrong here. Okay, I'll just take my word for it. Everything we've done is correct. So we have a problem in theory. Problem in theory. So what is our problem in theory? Anyone? Yeah, well, so yes, exactly. The circumference of these circles is not working, so the question is why? So the whole point is, so obviously it's not going to be the same here, but when delta x gets small, that's what the integral does. It makes delta x really small. Why doesn't it work? So I'll make delta x small. And I want you to pause before you get, okay? I'm going to make delta x small. And so notice we're taking all of the, what are we accumulating? What area are we accumulating? We're accumulating the area of these like gold bands, right? And the edges of those gold bands are what? Parallel to the x-axis. And what's wrong with that? There's a problem with that. No matter how small we make delta x, we're still going to be summing up a bunch of little segments that are parallel to the x-axis, no matter how small those things get. When what we need is, what do we need? Not perpendicular. So I'm going to make it big again. So here's like our dx, and then here's like dy. So dx is not the ticket for getting the surface area according to the circle. What else is there? What else would match the circle better? We did it last time. Yeah, the hypotenuse. And what is the hypotenuse of that triangle? Remember? ds. ds is the ticket to get this. So when that gets small, so rather than having these like perpendicular ribbons, like the edge is perpendicular. So this is like accumulating little changes in x. No matter how small we make delta x, those changes are still parallel to the x-axis, and they don't follow the curve. They don't follow the curve to get us surface area correctly. Instead, we need something like this. With little ds's being the edge instead of dx. And then when those get small, those will fit. Let me show you. So compare this to what I just showed you with the perpendicular, the dx's. So this is using the ds type ribbons. So there's a big delta x, and then here's a little bit smaller, delta x of 0.5. And then here's delta x of 0.1. So do you see how those ribbons are going to form the surface area eventually when delta x gets super small? As opposed to the dx will always be like a stair step, right? The dx ribbons going around will always be stair, and then we'll never, and that's why they don't give us a big enough surface area. We got way too small, 44 as opposed to 56. Okay, so that means we need to alter our rate of change function. So these things actually come from cutting a cone. So if we come up here, if you take a cone and you chop a piece, where's pause? It's right there. Pause before it, right there. So if you take a cone and you chop a piece of a cone, do you see that that's kind of the same as what we need? It's just on its side now. This is that ds that I was showing you over here. And then here's like the radius. So if you imagine that thing turned 90 degrees, it's like the shape that we would need for our football or a sphere. Okay, so we're going to take that thing and we're going to flatten it out so that we can get its area. Right, so we want surface area, we want a little bit of area of that. So we're going to take that thing and cut it and flatten it out on the paper like this. And when we do that, where am I? We get this thing, all right? So the distance around, it's still 2 pi r, that was still right. That was still part of it, but not times dx. Now we want it times this ds instead of dx. Okay, so it's going to be the 2 pi r times the ds is going to give me the area of that gray, and that's the area, the increasing area of that, what we call frustum. I call them ribbons, but so. It's got a, when you wrap it around, it's got an angled edge, not a perpendicular edge, right? And that's called a frustum. So the area of that gray region then, it's just like a bent rectangle. So it's base times height. So 2 pi r times ds is the area of that rectangle. And so what's ds? ds comes from our arc length. That's the square root dx. So what is the rate of change of arc length then? If ds equals this whole thing times dx, then rate of change is? It's not going to be happy when I try to write. We'll try. I'm zoomed in, that's why. So which is the rate of change? If ds equals this whole thing dx, then rate of change is? That whole thing without the dx, right? ds equals m dx now. So that thing is our rate of change. So we were right about the 2 pi r, except it's not times dx, but it's times ds on the angle. And so that makes this the new rate function. All right, let's do it. Let's see if we can get the area right. So we're going to go back to our GC file. Or volume, I mean. Okay, so I need to change this and do what to this? I'm going to change the rate function. I'm going to add what? Include square root of 1 plus. Right, this is the rate, exactly. So I want the derivative. F. T, and then this thing. So when I put a square on this, what are we expecting then? We expect this to equal the one we trust, right? We trust that formula up there as the half of a surface area of a sphere. So it should be equal to 0.3 when I put the square on. Got it. So this is like converts from dx's, what I'm showing in that picture, to using this is our arc length kind of transformation, right? So this transforms from dx to ds and gives us these types, these frustrums, right? Instead of the perpendicular ribbons. And those are the ones that will give us the surface area, accumulate surface area.